Good morning, everyone. Okay, today is the lecture number 8 of this advanced concept in steel technology, and we were discussing about the strengthening mechanism in crystalline materials, basically for steels also. So we have already covered about those strengthening due to grain refinement and strengthening due to solid solution, right? So we'll continue with that. We'll discuss some phenomenon today where there is an interaction between, or which is the consequence due to interaction between solute atoms and your dislocations, right? So you understand that means the field around the dislocation will interact with the field around the solute atoms, right? So that is one of the result of that is solid solution strengthening, as we have discussed in the earlier class. So today we'll discuss about this upper yield point in mild steel or low carbon steel, or in other some alloys like aluminum alloys in plastics. This upper yield point phenomenon is seen basically, or there is a ludar there is a ludar elongation, ludar extension, and or you can say yield elongation. So these are certain phenomena which we basically see in mild steel, or this is basically low carbon steel, that means ferritic steels, huh? Or we can see in the plastics, or we can see this in aluminum magnesium alloys, aluminum zinc alloys, and certain metals also, right? Upper yield point phenomena. And we'll also see this strainaging phenomenon, and the one is dynamic strainaging phenomenon. We'll see this kind of thing due to this interaction between your solute atom and dislocation. Okay, fine. We already seen a engineering stress versus engineering strain plot for normal steels or normal metals like aluminum or anything, right? We haven't seen any yield point phenomenon over there, right? Basically, we haven't seen that. But if we draw a stress versus strain plot like this is basically a load versus elongation plot. Okay, fine. You can convert the load into stress and elongation into strain. You know that stress is force by area, and elongation is change in length by original length, right? You can convert that into stress. So you'll get this kind of curve. This kind of. So you can see here, this is the upper yield point. That means if you look the normal stress strain curve, basically we see what the curve will go like this, and finally it will become strain hardened, and finally fracture will occur. But here what happens, the stress will increase to a maximum value initially, that is called upper yield point. From that it goes down again. The stress will decrease. And where it will reach, that is the lower yield point. So basically we can see we have an upper yield point where the stress required to deform the material is very high. Again, the stress will drop to a minimum value, that is called lower yield point. And we'll see serrations in, these are called serrations in stress strain curve. But inside the material, this is technically called yield elongation from here to here, or ludar extension, also called from here to here. It is called ludar extension or yield elongation, where we can see mountains and valleys kind of thing. That means stress goes up, goes down, then goes up, then goes down, goes up, goes down, like this, up to certain extent. Then finally, from here, we can see strain hardening occurs again, like normal cases. Continuous homogeneous deformation is there. This is actually a heterogeneous deformation, you can see. From here to here, this is heterogeneous deformation, right? Here, this is homogeneous deformation continuously, you can see. So now you can see, if you look into the specimen of the tensile test specimen, we can see these kind of things, these kind of bands actually. These bands are actually called Ludar bands. You can see this part is annealed metal, right? This part is annealed metal. That means you understand, uh, when we apply load on the tensile specimen, which shows this kind of phenomenon, upper yield point and lower yield point. In that case, what happens? Initially, there will be no uh, what homogeneous deformation will be there. There will be heterogeneous deformation. That means some part of the specimen will get yield, and rest of the specimen will not get yield, right? So a boundary will form, right? A boundary will form between the yield and unyield part. That is basically Ludar bands. Hmm. So what happens actually? What you understand? That means some part of the metal will get yield and it becomes strain hardened. So the portion which is ahead of that will start elongating and it will become strain hardened. Similarly, it will stop yielding. Then the portion which is ahead of that portion will start yielding. So this will be you can understand, this will be a heterogeneous kind of deformation happening inside the materials. And this Ludar bands will form, and finally you can see it will propagate. This is propagating in this direction, this is propagating in this direction, and you can see they are moving closer, and finally it will cover whole materials. After it will be over, when the Ludar bands will cover whole materials, then homogeneous deformation starts. That means strain hardening will start. All the part of the material, all the portion of the material will yield now continuously. Hmm. So this is all about your yield point phenomenon. Upper yield point, lower yield point, yield elongation, or this is called Ludar extension. Then upper yield, then strain hardening. Finally, fracture will be there. So you can see this one, same curve we have. Okay, let us look at the videos. Let us look at the videos. अरे सुना एक एक पूरा इससे कैमरा फ्लैश कैमरा की असली नहीं कैमरा आपको तो सेट की रहती पूरा ये ला सकते बड़े आओ बटे वो ध्यान में था वो कैमरा को नहीं चल रहा तो मतलब सेट अब लोग चालू चलेगा कमर टू कम Okay, fine. I think this video is available right now. Just look at this video. That will show you this Ludar bands, Ludar extension, Ludar bands in some materials. Just look at this video. Just carefully look at this video. You can see Ludar bands have formed here and here. Now you'll see it will propagate slowly, and some other Ludar bands may form in between them. See, these are the Ludar bands forming, and they are propagating throughout the materials. Because basically, this is a stage where heterogeneous deformation is happening. Once this Ludar band covers whole materials, finally, the material will yield uniformly. These Ludar bands are also called slip bands or stretcher strain marks also. Just look at the propagation. Just look at the propagation, how they are propagating.
कैमरा नहीं चुने
Again, just look at these bands, how they are propagating. Okay, I think you people have seen. I will close this video right now. Okay, fine. So now you can just see, this is a very beautiful image we have. We can see these are the marks. These are called stretcher strain marks, due to formation of these lunar bands. So you understand the surface finish is very poor here, in the materials. We'll discuss again this one, the same stress versus strain curve. You can see these are this is upper yield point. This is a heterogeneous deformation happening, yield point phenomenon. You can see upper yield point, small upper lower, small upper lower, this kind of things. And you can see here, initially this is your materials, which is given a tensile load. You can see a band is forming. This first lunar band is forming. It will start propagating in this direction and in this direction. Again, after some time, some and the lunar band is forming. This has already extended up to this, and the lunar band is forming here. You can see this will also extend downward and upward. Finally, you can see on further loading, you can see this lunar band has grown up. This lunar band has grown up more, and this is the third lunar band which is forming here. This will also grown up. And finally, a time will come when all the lunar bands have uh, covered whole materials. Right? All lunar bands have united here. They have propagated and covered whole materials. Now just look at this image. If you people have remembered this one, this is the dislocation. If you remember, this extra half plane of atom having a compression field, having a tensile field over here, and you understand. Now the question is, obviously, now the question is, why we have this upper yield point phenomenon and a lower yield point phenomenon, and why we have this kind of serrations, up down. Stress is increasing somewhat and decreasing somewhat, like here in this case, for example, stress has increased and decreased, then increased and decreased, then increased and decreased. But initially we have a very high uh, yield point phenomenon, upper yield point, and this is lower yield point, and stress is continuously increasing and decreasing up to this much. So why this is happening? Actually, this is happening because of solute atoms. When the solute atom will interact with the dislocation, this kind of phenomenon is basically seen. Which kind of solute atom? Basically carbon, nitrogen, boron, which are very small, basically interstitial atoms. These are not actually substitutional atoms. When we have carbon, nitrogen, boron, which are very small atoms in a steel, basically you understand ferritic steels or very low carbon steels, or this kind of phenomenon is basically seen over there. Why? Because you understand, around a carbon atom or nitrogen atom, we have a compression field, right? Because the size of the carbon atom, nitrogen atom is bigger as compared to the void size. We have a compression field. But here below the dislocation, at the dislocation core, we have a tension field. So what happens? This you can see, this is a very good example. Here you have a carbon atom sitting in the interstitial position, but it will get attracted to the dislocation core. So around this we'll have a compression field, but here we have a tensile field. So this will get attracted, it will get diffuse and reach over here, so that the strain field will be cancelled out, or the dislocation will become somewhat stable. Fine. So you can see this is this carbon atom or nitrogen atom sitting over here in the interstitial position is diffusing and going over here, right? So finally, what happens if you reach over here? It will pin the dislocation over here. Pin the dislocation means the dislocation cannot move easily right now due to pinning of the dislocation by this solute atom, carbon, nitrogen, boron, small atoms, right? Now, once you understand, once this dislocation will be pinned, you require more stress or require more load to make the dislocation propagate again, right? So that is why we have an upper yield point phenomenon here, right? Because the stress required to move the dislocation is very high, so we'll see an upper yield point. Upper yield point means the stress is very high here. But the moment you understand that you apply more stress to move the dislocation will get rid of this interstitial atom, carbon atom or nitrogen atom, right there, right? So dislocation will again start moving easily. Then the stress required to move the dislocation will be less. So what happens? This stress will, the curve will fall down like this, and it will reach to the lower yield point phenomenon. So what happens exactly again? Again, what happens? This dislocation will again pinned by this diffusing nitrogen or carbon atom. It will again pin off the dislocation. So that's why the stress is also more. You are applying more and more stress, right? Or you can say more load you are applying, but dislocation is moving. Again, it will pinned by the solute atom. So what happens? The stress required will be more. So there is a rise in the curve. You can see the stress is increasing. Again, it will be unpinned. So that's why the stress is going to go down. Again, the dislocation will pinned by the solute atom. The stress will go rise. So there is again it will be get rid of the solute atom. The stress will fall. So this is a discontinuous thing. You can see. So finally, when the stress will be very high, again there will be no yield point phenomena. There will be a strain hardening effect. And go to the maximum value UTS, and finally necking happens and it will fail. So technically, this is people call it Cortal Atmosphere in basically for steels. That is an atmosphere of solute atoms like carbon and nitrogen at the dislocation core of the dislocation, right? Which pin the dislocation. The dislocation movement will be hindered. It requires more stress to move again. So that gives rise to this upper yield point and lower yield point phenomenon. And this serrations also. Serrations means you understand pinning and unpinning, pinning and unpinning, pinning and unpinning like this. And another interesting point I would like to say, you understand about the upper yield point phenomenon and lower yield point phenomenon, why it is seen in case of this low carbon steels or in other materials, right? Like aluminum, magnesium alloys, aluminum, zinc alloys sometimes, and some other metals like titanium, cadmium. But why this lunar bands is seen? We'll discuss that. What is the why it is seen? You understand what happens exactly in certain materials like in plastics, or as I told in ferritic steels. What happens? The dislocation motion is not easy actually. What I mean to say is, see, dislocation will propagate and dislocation movement will start. These are two things. That means in certain materials, what happens? Plastic deformation is difficult to initiate, but once it will initiate, it will propagate easily. So in those materials, this kind of lunar extension is seen. So I have written here, in certain materials, plastic deformation is difficult to initiate, but once it initiates, it will propagate easily. Right? So yielding initiate locally in a region which then hardens. Further deformation therefore occurs in a softer material ahead of this. The yield region, the propagation across the sample, the boundary between the deformed and undeformed part is lunar bands. Right? And yield point, okay, it is talking about this A, this part. The yield point A in this steel is attributed to the pinning of the dislocation by the carbon atoms. The stress to unpin is greater than that to propagate the dislocations. That's why we are getting an upper yield point here. So understand this? Okay, so I think this part is clear. You don't have any doubt up to this? Now, as we have discussed, we have another phenomenon that is called strain aging phenomenon. Hmm. So this term itself is saying, strain and aging. There are two things here: strain, aging, right? Strain means, you understand, when we deform a material plastically, that is called strain actually. Hmm. I'm giving strain to the material. My material has undergone strain because I am deforming the material plastically. That is a strain in the material, right? Aging means always, that means we allow a materials to be there for a particular duration of time at a relatively low temperature. Hmm. Or relatively in the room temperature itself, will allow the material to remain over there without any deformation or without application of any load on the materials, right? So that is called edging phenomenon. So we have two things: strain and edging. So that means, you understand, we'll give a strain to the material, we'll deform the material plastically, then after sometimes we will unload the materials. There will be no load on the materials after deforming it plastically. Then I will allow the material to remain at a relatively low temperature for few duration of time, like some hours, some minutes, like that. So that will give rise to a strainaging phenomenon. So what is exactly that? We'll see. Okay, fine. I have mixed these points. We'll discuss that soon after discussing this one. You can see cold working of the materials. That means I have deformed the material plastically. Then after removing the load, I will heat it to at a relatively low temperature for a particular duration of time. Hmm. Then again, upon loading, more stress is required. Why? I have told you again, that means again yield point phenomenon is seen in the material due to increase in the strength and decreasing in the ductility. This is keep on continuing always if load is removed, and after some gap, if load again load is given, yield point is often in the materials. So that means we will have this kind of curve. You can see stress versus strain curve. We can see I am unloading the materials, and I am seeing a upper yield point, then I am seeing a lower yield point, then I am seeing a serrations, then I am seeing a what, strain hardening effect. But here, after taking the material to this point, I will unload the materials. So you can see I am doing unloading. Then after doing unloading, I will allow the specimen to be there at a relatively lower temperature for a particular duration of time. So after sometimes what happens, I will again load the materials. I'll apply stress on the materials or apply load on the materials. You can see this is the graph. You can see what is happening. You can see that means the stress will start from here. For low, you can see this will go rise, and you can again see what, again you can see a upper yield point phenomenon here and a lower yield point phenomenon. Then again strain hardening. So this will keep on. If you again unload the material, for example, right? If you again unload the material from here, for example, and you allow the material to remain there for a particular duration of time at a relatively low temperature, again you apply load, you'll again see a upper yield point phenomenon. Right? So this will keep on happening like that in the material. That is called strainaging effect. This happens, you understand, again due to the solute atom, carbon atom, nitrogen atom, diffusing towards the dislocation score and pinning the dislocation over there, for which we require. So you understand, that means heating the material to a relatively low temperature helps in the diffusion of carbon and nitrogen atoms into the dislocation core. Right? That's why this is called edging phenomenon. Now we'll see again. We'll continue with the same topic, that is yield point phenomenon, and what is the problem with that. So you can see the problem associated with this Ludar band in the materials. So yield point phenomenon gives rise to Ludar bands, we have seen. And what is the problem with Ludar band phenomenon? As I told, we'll see stretches strain marks or stretch marks on the surface of the materials on the on doing sheet metal forming, which leads to the poor surface finish. So this is the problem actually. We'll have a stretch strain marks, we will have a stretch marks on the surface of the material, due to these Luda bands, and the surface finish will be poor, and the customer will not buy this kind of materials, obviously, because of the poor surface finish. And another problem is what, we have to apply a putty on the surface on the material before doing actual painting on the materials, right? So this kind of problem will be there if Luda bands will be there. Right? What is the solution to the problem? The solution to the problem is either we can get rid of these interstitial atoms like carbon, nitrogen from the materials, right? So that they will not diffuse into the dislocation core and pin up the dislocation, right? That is one of the solution. That solution can be get rid of by adding some strong carbide and nitride forming elements like aluminium, vanadium, niobium, titanium, boron. These elements will form carbides and nitrides. So due to formation of strong carbides and nitrides, we can get rid of those uh, pinning effect by these solute atoms, carbon and nitrogen. And the solution is what we can do. We nowadays, basically this is for low carbon steels or plain carbon steels or mild steels. We are not using these kind of steels for making automotive components or automotive bodies. We are using nowadays IF steels, that is called interstitial free steels. Interstitial free steels, that means these steels are free of these interstitial atoms like carbon and nitrogen. Right? So if there will be no carbon and nitrogen atoms, we'll not able to see these kind of effects. We will not see these kind of bands, Luda bands in the materials. So these are the two solutions to the problem. Now we'll see same the strainaging phenomenon, and we'll see this kind of graph. And again, there is another effect due to interaction between the dislocation and solute atom. This is dynamic strainaging. We have discussed about strainaging, but now we'll see the dynamic strainaging. Here, what happens? The ductilities get affected to a large extent. So, can you people figure it out? What is happening? This is a stress axis. This is a strain axis. And you can see many curves. This is one curve, this is another curve, this is another curve, and this is another curve. Can you figure it out? The difference between this curve, this curve, this curve, and this curve? And something is written over here. Can anybody figure it out? What is happening in? We have talked about strainaging, you understand. Now this is dynamic strainaging. So what is happening here? Something is written over here. You have to figure it out.
Sir, at intermediate temperature, repeated
Yes.
yielding occurs,
Yes,
but at
yes, yes,
high
yes.
temperature, there is.
Continuous yielding. Yes, very good. And
Yes.
what about room temperature? Same continuous yielding is there also in the room
Yes.
temperature. At room temperature, continuous yielding, and at high temperature, continuous yielding. But at intermediate temperature, like 100 degrees centigrade or 200 degrees centigrade, these serrations are again, we can able to see this yielding effect, yield point phenomenon effect, or these serrations we can able to see again. This happens actually because why you understand, at this temperature, basically, the diffusion is good. You can understand the diffusion is good. The carbon and nitrogen atom easily diffuse to the dislocation core and pin the dislocation. So again, we have a this kind of phenomenon, right? But at high temperature, the yield strength is poor. Dislocation can easily move. There is no problem, right? Stress required is less. So it is the dislocation can easily move here. Dislocation can easily move here, but here, this is you can understand in this part. This is like your uh, police and thief kind of thing. Police is catching the thief. The thief cannot move. Again, the thief is moving, and again, police is catching the thief. Like this. This is the kind of game happening over here at this temperature, 100 to 200 degrees centigrade. Right? Okay, I think there is no doubt. If you have any doubt, you can ask me right here. If you have any doubt in the previous class also, you can ask me about these things. If you have any doubt, you can ask me. So I think you people have understood the strengthening mechanism by solid solution, strengthening mechanism by grain refinement, right? Okay, I think I have also discussed about in which conditions, in which environmental conditions, toughness is required in a material. Hmm? Can anybody tell me quickly in which environmental conditions toughness is one of the measure criteria which should be there in the material? Hmm? Hmm? Nobody is saying anything. Environmental condition means I am talking about temperature, pressure, and all. Pressure is atmospheric pressure, that is fine, but I am talking about temperature. Hmm? Okay, which
Sir, at high
yes,
temperature.
high temperature toughness is important mechanical property. Okay, do you people agree with him? Do you people agree with him that this at high temperature toughness is one of the important property? How many of you have remember what is the definition of toughness? How many of you have remember the definition of toughness?
So that combination of ductility and strength.
Yes, combination of ductility and strength. But this is in a layman words. But what about the proper definition?
So the energy absorbed
Energy absorbed.
up to fracture.
Energy absorbed up to fracture. Okay, fine. So what exactly it means? Energy absorbed up to fracture means? Tell me in a common way. Energy absorbed before fracture means what? Can I get any answer from others?
Sir, that the material plastically deform without fracturing.
Yes, yes, yes. Very good. So you that means if a material is absorbing more and more energy before fracture, that means it has high toughness or low toughness.
High toughness.
Yes, high toughness. So now, can you people again tell me in what atmospheric conditions toughness is an important mechanical property? Suppose I am taking a material to a very low temperature. Suppose I will take a steel and I will take the steel to your Arctic or Atlantic oceans, where we have icebergs. So what will happen to the steel in Arctic and Atlantic part of our world? What happened to the steel? Nobody is saying.
Toughness will decrease in Atlantic
Yes, yes, very good. Why? Why it will decrease?
because due to low temperature. Hello,
Yes,
hello.
Tapas. Yes, yes, Tapas. I am. You are audible. You can speak.
Due to low temperature, ductility decreases.
Yes, yes, very good. Due to low temperature, ductility decreases. What is that phenomenon called? What is that?
Energy.
What is
Hello.
that phenomenon called? Anybody want to speak something? What is that phenomenon called when the ductility decreases in a material at a particular temperature?
Brittleness.
I am asking about the phenomenon, or what is the term called brittleness. I understand. There is a temperature below which a materials will behave as brittle rather than ductile. So that temperature is called ductile to brittle transition temperature. Yes or no? Have you people recall this
Yes,
one?
sir.
Yes, sir.
Yes, sir.
Yes, sir.
Yes. So now you people are agree with Vijay as he told that at high temperature we need toughness.
Yes, sir.
No. You people are agree with Vijay. Vijay is saying that we need toughness at high temperature. Toughness is one of the important property at high temperature. Still, you people are agree with him, or you want to change your answer? Nobody is saying anything. Bishwajit, can you tell me in which atmospheric conditions toughness is most important mechanical property? Bishwajit Sahu,
Yes, sir.
what is the answer? What is your answer? Okay, Gitanjali, can you answer this one?
No, sir.
Gitanjali.
No,
Okay,
sir.
Manas Ranjan.
I think no, sir.
No, sir. Okay, Mansi.
At low temperature,
Yes. Why low temperature?
because the phenomenon ductile to brittle transformation is low, matlab, means toughness is low at low
Yes,
temperature.
yes. Yes, Shweta is right. Okay, very good. So I am saying I have given you a lot of hints. Still, you people are not saying. How many of you have seen that movie, Titanic movie? I think everybody have seen that at least 2 to 3 times. Yes or
Yes,
no?
sir.
Right? So what
Yes,
happens
sir.
to the ship? What is the main cause of drowning of the ship and dying of a lot of people over there? What is the reason behind that? How many of you have remember why the ship has drowned? What is the main reason behind the sinking of the ship, Titanic ship?
Due to failure of body.
Due to failure of body. How the body get failed? Failed means that means you don't tell me fail, but failure and fracture is different thing. Fracture has happened or failure has happened?
Fracture.
Yes, fracture has happened. So a crack formed, huh? So why that crack had formed? I mean, what is the main reason behind the formation of that
Because
crack?
of
Hmm. Hmm, hmm, hmm.
because
Yes,
of
Mansi.
transformation of austenite inside. Because of
Transformation.
transformation of austenite to martensite at low temperature.
Okay. Uh, so do you think that the steel is made up of austenite? Are you sure about that? That is an austenitic steel? I'm not sure actually. Okay. Anyways, the thing is what the sheep has collided with an iceberg, right? The sheep has collided with an iceberg. The moment it collided with an iceberg, So the sheep should have a property that it should absorb the energy. This is my answer, huh? The sheep has collided an iceberg, right? So the moment it collides, the sheep should absorb a lot of energy of the collision. So and it should not get fractured. But what happens? It cannot able to absorb the energy. Rather than it got fractured. This happens because sheep, the material is made up of steel, and that steel has become brittle due to very low temperature prevailing over there. Right? Due to brittleness of the steel, it cannot able to absorb the energy. So you understand what is happening. The toughness was low in that condition or high in that condition when it got fractured.
Low, sir.
Obviously
Low,
low.
sir.
Well, obviously that's why it gets fractured. Due to this ductile to brittle transition happens. Because people earlier days they don't know about this ductile to brittle transition happening in the materials, right? So that is the reason, right? The crack have initiated and the water has gone inside and it will get synced up. So toughness is very now. What is the answer? Vijay, what is your answer right now? In which atmospheric condition toughness is most important?
Sir, at low temperature.
Low means very low temperature. You can say, right? Okay. What is the difference between failure and fracture? How many of you can see? Tell me what is the difference between failure and fracture?
Hello, sir.
Yes.
Before fracture, there is a indication we get before
Okay.
fracture.
Hmm.
Case of failure, there
Okay. What
is
is the definition of fracture? Can anyone tell me how you can define a fracture? How you can define a fracture? It's very simple. There is no.
A particular material is fractured into two or more pieces.
Yes, if a single material will be separated into two or more pieces, that is called fracture. Has happened. Okay, very good. Okay, see, you people should not be confused between fracture and failure. Huh. Failure actually means it is in broad way or broad term. We are saying failure. Fracture is not in broad term. Suppose for a design engineer who have designed a steel, for example, for a breeze application, right? For a breeze application, the design engineer has designed the steel. But what happens? The breeze is getting bent. Suppose it is a bending phenomenon has happened. So that is called failure of the breeze. I'm not talking about the breeze has broken down into two parts or many parts. It has just bent. The bending of the breeze has happened. So that is the failure. You understand now? So that bending is happened means there is yielding has happened. Yes or no? Am I audible?
yes,
Yes, sir.
yes, sir.
That means yielding has happened. But design engineers design a material on the basis of yield strength. I told you many times. He designed the material on the basis of yield strength. Yield strength means the stresses or the load on the breeze should not be above the yield strength. But during the application, the breeze has bent now. That means some yielding has happened. So that is a failure. But if the breeze will separate into two pieces completely, then it is a fracture. Right? Similarly,
Sir,
while yes.
sir, Manila ma'am classes.
Okay, I'll take 2 minutes more. Then second example I can give you, like suppose necking is happening in a materials. Suppose if fracture hasn't happened, necking has happened. That is also a failure. Failure have started after UTS. The material start necking down, right? So that necking has happened means that is a failure again. But after failure, if the material will goes to the fracture stress point, then that is a fracturing of materials. It will separate into two pieces. Okay, I'll stop here. We'll continue our lecture from the next class.
Sir,
Yes.
the low temperature toughness means below 0 degree.
Below 0 degree, it is not like that. Below 0 degree, there is a particular temperature for a particular materials, right? There is a particular temperature for a particular materials. If your material is very ductile, that doesn't mean that at 0 degree centigrade it will become brittle. See, I am talking about Arctic and Atlantic conditions. You understand the temperature is minus 40 like that.
Yes.
Yes. So there is a temperature. You should check. You should go through today and tell me what is the ductile to brittle tension of steels. Different steels, austenitic steels, ferritic steels, and martensitic steels, and your plain carbon steels. You have to check it and you have to tell me in the next class at least what are the different temperature at which the material become brittle.
Hello, sir.
Basically,
Hello.
yes. Basically, below 20 degree, minus 20 like
Sir,
that. Yes.
sir, one
Minus
question.
20 or minus 30.
Sir,
Yes.
at
Hmm.
absolute temperature, what happening in the properties of steel at absolute temperature?
Sorry.
Any changes? Hello,
Absolutely.
sir.
Obviously,
At
absolute. See, first question is if you in the thermodynamics as we have discussed, there will be we cannot reach to the absolute temperature first. It is not possible to reach to the absolute temperature. Never. There is no device which can take us to the absolute zero. It is the lowest temperature possible for us, but we cannot reach to that temperature. Even if you are taking the material to a sub-zero temperature, which is near to the minus 193 like that. Liquid nitrogen temperature. Obviously, the materials become completely brittle. It will become completely brittle, and the strength will be like toughness is, you can understand it is very low. Toughness will be very low. It will become completely brittle. The fracture will happen is completely brittle fracture.
yes, sir.
It can, yes. Yes. Yes, Tapas, you want to ask any question?
No, sir.
Okay, you people can leave.
Thank you, sir.